Okay, I'm so pleased to present Laura Vega. Before I give her bio, I just want to give her a big thank you for doing this tonight. And I also want to thank Emily Callahan, who is my sister from another mother's daughter and works at the University of Maryland with Goddard Space Center, who got me Laura Vega to speak tonight. Thank you, Emily. Okay. Dr. Laura Vega is a postdoctoral researcher at NASA's Goddard Space Flight Center and at the University of Maryland, College Park. Laura obtained her bachelor's degree in physics from the University of Texas at San Antonio in 2013. She is a former student of the Fisk Vanderbilt Master's to PhD Bridge Program, where she earned her master's degree in physics from Fisk University in 2017 and PhD in astrophysics in 2021 from Vanderbilt University, which sounds like an amazing program. So take it away, Laura.
Okay, I was trying to find my unmute button. Hello, everyone. Thank you very much for this invitation. And thanks for joining tonight. I'm excited to share with you some work that I did for my PhD. And this picture here shows just a rendition, artist's view of what we think these stars look like. So I'll be talking a little bit about the background of these stars and then some projects that I did. But first, I would like to give a shout out to my PhD advisor, Kevin Stassen, and research mentor, Rudy Montes, who helped me throughout my PhD program, as well as NASA and the Smithsonian Latino Center. And now I am a postdoc fellow at Goddard. So just to paint a picture to get the background, we're going to start with this very basic diagram of stellar evolution. So we know that all stars are born in huge clouds of gas and dust, and their initial mass determines their ultimate fate. And I'll be focusing on stars that are low to intermediate mass stars, in particular at late stages of their evolution. So in particular, before they become planetary nebula. So at this stage, they are known as post-asymptotic giant branch stars. And during this phase, they're experiencing huge thermal pulses, ejecting their outer layers as they become unstable and they dissipate into their environments and become planetary nebula. So here's just some beautiful pictures of planetary nebula taken from Hubble. As you can see, most of these are spherical, at least in the top row, but the bottom row show different formologies and shapes and exotic configurations. And we want to know why, because it's still not well understood. Some theories are that is because of strong stellar winds or magnetic fields and also binarity. So some of the open questions are that binary interactions affect the evolution of stars like the sun. And this is especially true in evolved stellar stages where the increased size of these stars make the binary interaction more significant, moving this material in their vicinity. So one of the questions is, how does binarity affect these late stages of stellar evolution? So some of my project focus was to combine a variety of data from different sources, such as the Kepler Space Telescope, historic light curves spanning more than a century, submillimeter data, radio velocity measurements, and X-rays. So a little bit about RV tau variables. So they are a class of stars that are named after their prototype RV tau, as shown here. And it's actually in the Taurus constellation. They have a very peculiar pattern in their light curve. So this is a brightness over time, and their pulsations show this deep, shallow alternating pattern in their light curves. They're rather cool stars, about 5,000 to 6,000 Kelvin, and are known to be in binary systems. So here I'm showing the HR diagram and the location of these orbital stars, which show that they're very luminous, about 1,000 times the luminosity of the sun. And they're in a location where massive evolutionary tracks and lower mass evolutionary tracks meet, though the lower mass evolutionary track is more widely accepted in the community. But we don't really know how they become what they are now. Here's another rendition of the HR diagram, but this time with actual data showing some post-AGB stars, as well as orbital stars that have either a disk or that don't have, anyway. Well, the point here is that they kind of cross this instability strip. So this blue and red lines here show where these instability strip is and where stars become unstable as they evolve. Taking a look at the periluminosity relationship, also known as the Leavitt law, here we see type 1 Cepheids and type 2 Cepheids. RV tau stars are type 2 Cepheid variables, and we do see this relationship between their luminosity and their periods. Looking at the data, type 2 Cepheids are actually comprised of 3 groups. So the BL Hercules, which have shorter periods, pulsation periods, the W Virginis stars that have a bit more longer periods in the order of a couple days, and then we have the RV tau stars. So I forgot to mention, so this is the y-axis is brightness and x-axis is period. And the RV tau stars have longer periods that range between 30 to 150 days. There's a lot of them that show an excess of infrared light, which I will be talking about in a little bit. There are 2 flavors of RV tau stars, at least based in their light curves. So RVA type show the typical deep, shallow minimum based on their pulsations in the order of 20 to 150 days, depending on the star. But there's this other type, the RVB type, that has this longer term variation. We do see the pulsations, but this longer term variation in brightness varies between 700 to 2,500 days. And it was until recent that we didn't really know where this variation came from. Before I go on to that point, I would like to talk a little bit about the spectral energy distribution, which is just showing the amount of light, or it represents the amount of energy emitted at any particular wavelength. So for example, the black points are data from different telescopes at different wavelengths, and the black lines are models of the star. And the red points are depicting that there is near infrared light excess in these systems. And for RV tau stars and post-AGB stars in general, we know that near infrared excess is indicative of hot dust. So there is warm or hot dust around the star, very close by, and we think it's due to a disk. The disk is shining really brightly in the near infrared. When we see far infrared excess, we say that this is indicative of a shell. So warm dust that is dissipating into space. And there are post-AGB stars that don't have this infrared excess. So we need more data, they're uncertain, or they just don't have dust in their vicinity. So the Wide Field Infrared Survey was a survey that scanned the entire sky in infrared twice, snapping pictures of about 750 million objects, including remote galaxies, stars, asteroids. And so here's a map of the Milky Way galaxy, where we see that, so for example, here are the 4 different filters that the WISE instrument, and here's a little picture of the telescope, had on board, showing the different types of light that it observed. So the cyan represents the light emitted predominantly from stars and galaxies at the wavelength of about 3.4 microns. Green and red represent light mostly emitted by dust at 12 and 22 microns. And because we have these 4 measurements for a lot of stars, a group, Gezer et al., 2015, they collected data for all the post-AGB stars in the galaxy. And they found reference stars that were known to have disks by other means, other observations, and stars that had shell type SEDs. And they found that when they plotted these different stars in this space of, color diagram, so the filters, the 3.4 minus 4.6 filter and 12 minus 22 filters. So this is a color diagram. Anyway, these stars gather or collect differently. And they defined this as the disk box because they have hot gas. So they're kind of bluer. So hotter gas. And then these stars are shell objects. They have warmer dust, cooler dust. They looked at the RV Tau stars to compare with those reference stars. And so out of 126 stars, they knew that 19 were RVA. They didn't have that long-term variation, but the RVBs, all of them landed in this region that they defined as having a disk. And in this diagram shows in blue all of the objects that are confirmed binaries. So there's these connections that when you have a disk, you are probably a binary system too. So, and I'll get a little bit more into that in a little bit. So just to recap, RV Tau stars are very bright. They have this alternating deep and shallow minimum in their light curves due to pulsations. There's also an RVB type class that has a longer term variation. They have infrared excess in their SEDs, their spectral energy distributions. That's indicative of dust, either hot dust, warm dust. And they're either post-AGB stars or post-red giant branch stars, but they're evolved. They're all evolved binaries. And they have dusty disk, probably due to binary interactions. And so this next slide shows what we think is the pulsating system and its stellar companion, its binary companion, and they're inside this large inner rim, this large disk of material. So now I'm going to talk about DF Cygni, which I think is probably my favorite star, being that it's the first star that I studied for my program. And we published this work in 2017, where we showed that evidence for binarity, possibly due to the disk obscuring the binary system. So some quick facts about DF Cygni. It's pulsation period is about 50 days. It has a long-term period of about 800 days, the RVB phenomenon. And it also has an orbital period about very similar to the RVB period. And this measurement was taken from radial velocity measurements. So looking at the star's spectrum as the spectrum shifts. And Kepler, so DF Cygni was one of the stars that Kepler observed in its original mission. So Kepler launched in 2009, and its mission was to hunt for exoplanet stars. Its mission was to hunt for planets transiting stars, and it observed about 100,000 stars with high cadence for about 4 years. So every 30 minutes, it took an observation. So there was a lot of data. And here is the patch of sky that it observed. Here in the detectors overlaid on this image here, just to show where in the sky it observed for those 4 years. Here is the light curve for DF Cygni. You can see the deep and shallow minimum of the due to pulsations, and the line in the background is just the mean brightness of that long-term variation. So we overlapped the 2 cycles just to find a period, because that's all we have. And we found a period of about 800 days. In this next slide, I want to highlight the maximum the pulsations at maximum light, RVB max, the pulsations at minimum, and then again at maximum. Because when we remove the long-term trend, we get this flat light curve. So here in light curve A, we have removed that long-term period, and just to see what the pulsations look like. The light curve in B is showing the cycles, the pulsation cycles that we found in the light curve. So what we defined as a cycle is 1 deep, 1 shallow, 1 deep, 1 shallow. So we found about 29 of them. And the C light curve shows data from Kepler, individual Kepler quarters. So every quarter, Kepler had to kind of move around and its position. And so we had to adjust ourselves and shift the light curves. And so I think we did a pretty good job. But yeah, that's just showing the different data chunks from Kepler. The way we found the pulsation period was just a simple mathematical Gaussian model for all of in this case, we looked at all the deep minimum, and we used a Gaussian to find the pulsation period of about 49 days, which is depicted here as a slope. So this diagram here, it's like a time diagram where, the arrival time of the deep minimum as a function of the cycle. So the slope represents the period that we found. And here is, again, just the two, the light curve and the deep minimum together, showing the red data points, the blue and the red again. And the second panel is the residuals, when we subtract the model from the data. Now, looking at the data, so astronomers, we like to log everything. But when we look at the raw light curve, not logging the brightness, like in log units, we find this very peculiar thing going on where the pulsations at maximum are rather large compared to the minimum pulsations. And we were very curious as to what that was. We found that the amplitude of the pulsations decrease by about 90% from the pulsations down here, as well as the mean brightness. So this line and this line, there's a a 90% difference in brightness. So that was interesting. And I'll talk more in a bit. I'll show a little video. So again, we come back to the spectral energy distribution, where we have brightness or flux as a function of wavelength. And I keep doing that. So in this black line represents the stellar model for, the spectrum for the star. And we found these points that are very low. And we found out that they were actually taken during long-term minimum. So what we did was we pushed those points up by 90%, and voila, they do line up with the model. We also see that infrared excess in the near infrared, which is indicative of a disk. And so we showed that there is some obscuration happening in this system. So we inspired a group in Europe, so Kiss and Bodhi. They took all of the available American Association of Variable Star Observers, which some of you might be a part of. So AAVSO data, ASAS, Kepler, and OGLE for 15 RVB stars. And these light curves go way back, showing the long-term variation. So for example, here's DF Cygni. You can see the long-term trend. This little light curve here is the Kepler light curve. And what they found was the same thing we found for all of these stars, that there's a linear relationship between the pulsation amplitude and the mean brightness. And here is similar thing, just the pulsation change relative to the change of the mean brightness in the system. So we were happy about that. So we used Kepler ultra precise data for DF Cygni to look at the pulsations and the light curve of the star. And we found that obscuration is due to a disk pulsate or obscuring the system. And so here is a better way to, everything that I said, this is probably a much better way to represent what I just said. Here you have the pulsation, the pulsating star, the companion, and as the pulsating star comes behind the inner edge of the disk, it's being blocked by it. That's why the pulsations look smaller. And when it comes back up, well, also the RVB phenomenon only happens when the disk is inclined, so that you could see that long-term variation. For the RVA type stars, where you don't see that long-term variation, the system is probably face on, where you could see the binary all the time. So we looked at the second brightest RV tau. And this project, we published it in 2021 for U. And this is the star that we found X-rays from. So here's some properties of the star. This chart just shows that it's the second brightest of these RV tau stars. It's at 1.1 kiloparsecs. It has a pulsation period of about 46 days. It's about 5,500 times more luminous than the sun, 100 times more, the radius is 100 times bigger. There's a magnetic field measurement for this type of star as well. The orbital period is about 2,500 or 600 days. And we used a relationship to get the mass of the pulsating star. So based on this Greg, Grin, and Jurovic 2017, if we know the pulsation period, the luminosity, the temperature, metallicity, these equations can be used to estimate the star, the mass of the star. And that's what Bodhi and Kiss did. And so they found two measurements of 2 and 2.13 solar masses. We took the average of that just to see just to kind of experiment. So we averaged those two values as 2.07. The next thing we did was looked at the radial velocity measurements that Ullman et al. 2018 got. And these measurements are cleaned of pulsation effects. And what we did was we fixed the orbital period as the RVB period to see if we got similar answers. And it's within the errors. And so here is the radial velocity chart for UMON, and the model is in red. We found the mass of the stellar companion using this equation, and we found 2.2, so similar to the post-AGB mass. We also found the separation of the two stars, which was about 6 AU, a little larger than the separation of the Sun and Jupiter. And we found historical data from the American Association of Variable Star Observers, which is a global network of amateur and professional astronomers dedicated to look at their favorite star. And this has been going on since the late 1880s. And so there's a large data set for, oh, I just realized this thing's not done. Can you hear me better? So we also downloaded data from the DASH archive, the Digital Access to a Sky Century at Harvard. And this data is from photographic plates that have been digitized. And I think this project is still ongoing. They're trying to digitize 0.5 million photographic plates covering from 1880 to 1985. And I downloaded the data. I plotted the raw data here, showing data that goes back to more than 130 years. And what we did to kind of look at match the data, we converted the light curve from magnitude units to flux units using this equation. And so here we have the two data sets now more comparable, where the black points are from DASH and the gray points are from AAVSO. Zooming into this section here in the light curve, this is where the AAVSO and DASH data overlap the most. I mean, it's not perfect, but we do see where the DASH data points do get lower at minimum and higher values at maximum light. And to just look at the long-term variation of the light curve, what we did was we binned the data by the pulsation period. And so here's the light curve again, this time binned at 60 days. Again, the black points are DASH, gray points are from AAVSO. We also highlighted in golden where the AAVSO minimum were not as deep as other minimum. And then some values here where the two data sets overlap. We phased the light curve by the long-term period, which is shown here in the second panel, and we fit some parabolas just to see what it told us. And we see that there's two different minimum in this phased light curve that are from these highlighted points here. So in the past, we found that at least the minimum has disappeared at least twice in the past, with a time scale of about 60 years. Of course, this data is not, well, yeah, this is what we found in the data, about 60 years. And to look at it another way, we phased the light curve by 60 years, and we do see more similarities by this phase. So these two highlighted regions in the original light curve are shown here in the phase light curve that show that there's a lack of that deep minimum in these two sections here. There's also a deeper minimum right before those sections in the light curve. So we were thinking, well, what if something is eclipsing, or there's something in the disk that's orbiting at that period? So there's perhaps a warp that is about 25. We calculated that it could be about 25 AU from the binary system. So here in the middle, we have the binary, a possible warp in the disk, and then the extent of the disk was found or calculated by some submillimeter data that we collected from the submillimeter array in Mauna Kea. So this is just to give a sense of how big these disks are, which is actually larger than the distance from Voyager to the sun. To get that disk diameter, we used submillimeter arrays. We measured, or we modeled the data for these, and we found a disk diameter about 550 AU. Of course, more data would be better. Perhaps in the future, we'll be able to collect more data and kind of refine that disk diameter. But based on the images, this is what we got. We were also able to measure the inner disk rim radius. Won't go into too much detail, but we found that the inner disk radius would be about 5 to 9 AU. So this is where the orbit of the two stars would be located. And as a reminder, we found 6. The separation of the two stars was about 6 AU. It's comparable to what we find for the inner disk. And for UMON, we also discovered X-rays. So this is the first target that we see X-rays coming from an orbital or post-AGB star. And this data was from XMM Newton. The cool thing about XMM Newton is that we can get images as well as light curves, so time and energy, and a spectrum, which is a wavelength and energy. And in this next slide, I'll show the images for the source. So XMM Newton has 3 detectors: the EPIC PN, EPIC MOS1, and MOS2. And there's a clear detection here. We find a nearby source, so we extracted only the flux from within this inner circle. We fit the spectrum, and we find an X-ray emission of about 10 megakelvin, or a temperature with a temperature component of 10 megakelvin. So where do these X-rays come from? We don't know, but there's a paper that was published around that time that shows that there is H alpha emission coming from the companion star based on jets that are coming from the companion. And so we think that the X-rays could be also coming from the companion star as it gets closer to the inner edge of the disk. And so here is a video to explain or show that more clearly. So we have the companion, and it's kind of accreting material from the inner edge. And as it does, we find that it could emit X-rays, perhaps. We also think that, so we know from other studies that the companion might have a jet coming from it. And going back to our spectral energy distributions, we found data from the archive. The new data that we offer was the XMM UV data, these 2 points, and then these 2 points from SMA, which agree with literature data. And then here, this is a representative spectrum of the X-rays. So there's that other component that is present in this system. So there's this component, the stellar component, the infrared X's here from the disk. So now we know that this is a binary, has a disk, and now we know that it has X-rays. We also made a little calculation to see how much mass the disk of the system has, and we calculated that it's about 0.4 Jupiter masses based on calculation from Hildebrand 1983. And just to wrap up for UMON, well, actually, I already said this, so I could skip this. So in general, we demonstrated that the long-term brightness behavior of the RVB stars is due to disk obscuration, obscuration of the pulsating star, and it's fundamentally a binary star phenomenon. And we find X-rays are present at least in one of these systems. My research mentor, Rudy Montes, has worked with some students to look for other stars in the archive, but we haven't found any candidates yet. And some future work, we would like to continue in the search for X-rays. And we do have more SMA data, submillimeter data, to look at the disks for at least 5 additional targets. And we want to continue monitoring the long-term variation with data such from AAVSO and DASH. And with that, I'll leave you with this little video again. Oops. Well, I guess it won't play. But thank you very much for your attention.
Does anybody have any questions?
Yes, does anybody have questions in the audience here or online?
I have a question.
Yes, go ahead.
How excited were you to find the X-rays? I mean, that sounds like a huge discovery.
I was at first I didn't understand when my advisor told me, like, oh, this star potentially has X-rays. I'm like, okay, what do we do? And when I sat down with this and I was trying to look through the literature if there was any detections of X-rays in other targets, it was when it really kind of settled and it dawned on me, like, oh wow, this is very cool. So pretty excited.
Nice, that is exciting. Thank you.
Mm-hmm.
You have additional questions online?
Can you hear me?
Yes.
Yes, we can.
Okay. You kept talking about AGB stars. I forgot what the AGB stood for.
It's asymptotic giant branch.
Okay. Okay. I know that branch. Thank you.
Mm-hmm.
I have a question here in the
I have a
audience.
question. I'm trying to picture this system in my head, and the videos certainly help. Do you have any idea? Actually, first remind me what the masses. Do you know the masses of these 2 stars?
At least for this system, UMON, they're relatively the same. So 2 solar masses.
2 solar masses each.
Mm-hmm.
And is one of them like closer to the outer or the inner edge of the disk than the other? That's the one that's, or are they? This video is answering my question a little bit, I guess, if this is accurate.
Yeah, I think they're both perhaps could be touching like that inner edge or being very close to it at least. Yeah.
So they're both going around their common Berry center and then kind of clearing out what's on the inside of the disk. That's the model.
Yes.
We have another question. Go ahead.
Scott has a question.
Yeah, I have a question. Are any of these periods
like, especially the long one, the 60-year, is there precession that we're seeing from, from our perspective?
It could be precession. I didn't look too much into that, but that could be a possible explanation.
So what are the other possibilities, I guess,
Um,
especially the long period?
that's a good question. Off the top of my head, I'm not quite sure. Because since we saw this deeper eclipse or deeper RV minimum, and then a lack of the minimum, the long-term minimum, our first guess was, well, could there be a warp that kind of blocks light and then doesn't block light? There could also be perhaps a planet.
Yeah. Right.
Yeah.
Now I have another question. Early on, you were very happy to find the sort of 90% extinction of both the overall amplitude and the amplitude of the variations. Is that the clue that told you it might be a disk? And what were the alternatives if it wasn't that?
So the decrease in brightness from both that were very similar to 90%. I think that was the main reason why we thought it was disk obscuration, especially looking not only the light curve, but also in the SCD, where if these data points weren't available, then we would be like, well, we might not be able to say it's obscuration. But because these points were also obscured by 90% and were taken during minimum, that gave another clue. And so we were very happy to see that this other team found the same for these other RVB systems.
So I guess what I'm asking is there another mechanism when you're trying to figure this out? I'm not thinking just about what the final result is, but the sort of the excitement of figuring out what it is, which clearly you enjoyed. If it wasn't the same 90% for both, are there other mechanisms that you might have been thinking about before you sorted that out, and then that kind of nailed it down for you?
When I first started, we were kind of, I remember just one idea was kind of, there's this, like, I don't know how to explain it, but there's this bowl that is throwing water in it, and then it tips over and releases that water and then goes back up. And then again, I don't know what that device is called, but we thought something like that was happening, where there was something physical happening with the pulsating system.
Okay. Kind of like the dunking duck or something.
Yeah, something like that.
something gets up to tipping and then goes.
Yeah, something weird like that. But now, like, looking at it at a very basic explanation, like, oh, it's just obscuring the star. I'm like, okay, that's probably better.
Other
More
questions?
simple.
We have some more questions from our audience.
Yeah, how much
online.
of what we're seeing is simply a variability of the star itself, and how much is coming from the dust disk?
Well, that's the different periods, right?
Right. So and also how much is coming from the orbit, especially if they're eclipsing? Is that a possibility?
There might have been something, I can't recall if I did such a calculation. But I mean, we do know that it's inclined.
So it's not eclipsing.
Right. Yeah.
Right.
The stars themselves aren't eclipsing.
I
The
have a question.
shorter- The shorter period is the star's variability, and then the longer period is the dust disk obscuring, I guess.
Yeah. Yes.
So, may I ask a question?
Mhm.
If, you're essentially seeing attenuation when the star moves behind the dust. And then, when it moves back out into a visible region, it gets brighter again. Did you look at wavelength dependence in terms of that attenuation to get a sense of what is the composition of the dust and things like that?
So I know that there's H alpha measurements at long-term minimum. So if the pulsating star is being blocked during this minimum, then you'll be able to see the companion star. And that's where you're seeing I guess more alpha H alpha excess or emission.
Yeah.
Based on, but that's one of,
That's the extent of the data that you have at the moment.
yes.
Okay. It would be, I have no idea what you would find if you did look, but it would be really interesting to me to see what the dust is made out of.
Yes. Yeah, with more, I think with more SMA data from the submillimeter array, that could be answered.
Dr. Vega, I have a question also, just trying to understand the binary relationship there, because I assume that there would be equivalency of mass between those two objects, between the star and at least what, unfortunately, it may just be the way it's visualized in the video, but in regard to the smaller item, whoops, we got a problem here?
No, I'll just turn your video on.
Okay, that's fine. We're just doing a video adjustment here. So, thank you. Anyhow, so my question really comes back to is that you were sort of pointing out that this other object was accreting material, and I'm wondering whether essentially there's going to be a likelihood that the mass of that's going to increase, where all of a sudden it's going to attract its binary pair. And so I'm asking you if you had any thoughts as far as what the long-term future may be for that binary pair.
Since it's accreting material, but it's also releasing material as jets. What we think is that being that the pulsating star is in a binary system, its evolution might be paused or slowed down because of the binary. Yeah, I'm not sure. I think I need to think about it a little bit more. There are some theories in the literature that I'd have to go read up on again. But good question.
Are there any other further questions out there online for Dr. Vega? Anyone? There not being any here, I'm the audience also. Dr. Vega, thank you very much for your presentation.
Marvelous.
Thank you.
It's been
Thank you
great.
so much, Laura Vega. It was really interesting. I don't say that about every presentation.
Thank you
This
very
was
much.
A lot of fun. Thank you for doing this.
And if you have further thoughts, maybe we'll come back and do another program and then you can tell us something more about all this. We appreciate it
Yes.
very much. Thank you very much.
Thank
So
you.
this will be ending our program for this evening. And in a few moments, we will be closing the Zoom event. Thank you.